Here is a quick review of rotational motion as it compares to linear motion. Now, most of you have come to this chapter after kinematics and after studying linear motion. So the comparison will make it much easier for you. X in linear motion, measured in meter, is the displacement. That's what we call it. But in rotational motion, it's replaced by the angle theta, which is measured in radians. So x is replaced by radians. And then we know that velocity is dx by dt. Velocity is in meter per second. Angular velocity is in radians per second. You see that connection? Acceleration is in meter per second squared, while angular acceleration is in radian per second squared. Those are similar quantities. We also know that the length of the arc, S, is equal to the cross product of theta and r. Likewise, linear velocity is the cross product of omega and r. And acceleration is the cross product of alpha and r, in that order. So remember that the order of the cross product does matter. So in all of these three formulas, as you can see, r is on the outside. And then we come to the kinematic equations. We have this equation, the fundamental one, where linear final velocity is equal to initial plus at. You also have S is equal to V naught t plus 1/2 at squared. Another one that we have is V final squared is equal to V initial squared plus 2a delta x. Let me speed that up a little bit. So on the rotational motion side, you have these corresponding equations. You see that the linear velocity is replaced by the angular velocity. Displacement is replaced by theta, as you can see there. And then you have alpha instead of a. This is another equation that I tell my students to use, which is quite useful, where you take the average velocity multiplied with time to get the displacement in linear motion or the angle of rotation in rotational motion. So that is a brief idea of the equations in rotational motion. Now, another connection that we need to make is that in translational or linear motion, mass plays an important role. Mass is related to inertia. Inertia depends on the mass of the object. If the mass of an object is higher, then its translational inertia is also higher. That's why it's more difficult to stop an object that is heavy when it's moving. Now, when we come to rotational motion, although mass plays a role, definitely, the distribution of the mass from the axis of rotation is also important. So it's not just the mass, it's also the distribution of the mass about the axis of rotation that's important. So we combine these two quantities, which is the mass and the distribution and the distance of that particle from the axis, and we call it rotational inertia. So rotational inertia plays the same role in rotational motion as that played by mass in linear motion. So to get you a preliminary idea of rotational inertia, we can start with what we know in linear motion. Now, this was taught on day 2 of a particular session. That's why you see that. We will start with kinetic energy, which we know is 1/2 times mass times velocity squared, and then substitute for velocity as r times omega. And it's squared, that's why you have r squared omega squared. And that's because linear velocity is r times omega. And now we can consider a rigid object in which the distribution of the particles is continuous. And therefore, we can take the mass to be distributed uniformly. From there, it's possible to define sigma 1/2 mi ri squared, where I represents the ith particle. And omega, the angular speed, is the same for all particles. So if you have a rigid object and if it's spinning about an axis, any axis, the angular speed is going to be the same for all particles, and it's independent of the distance from the axis. Therefore, when you take that summation, and we're trying to find the total kinetic energy of the object, we can take the constant out. That's why you have 1/2 omega squared outside, and then we are left with sigma mi ri squared. Now that's important quantity. That sigma mi ri squared is called rotational inertia, represented by the symbol I. Now it's also called moment of inertia, so be careful about that. So that's a fundamental idea of rotational inertia. All right, now that we have some preliminary ideas of how rotational motion compares with linear motion, we can work out a few problems. So here is the first one. An astronaut is being tested in a centrifuge. It has a radius of 8.40 meter and in starting rotates according to theta is equal to 0.130 t squared. T is in seconds, theta is in radians, which are the correct units. And when t is equal to 2.60 seconds, we have to find the magnitude of the angular velocity, linear velocity, tangential acceleration, and radial acceleration of the astronaut. So what is given is a function that represents the angle in terms of time. And from there we have to get all these terms. We know that omega, the angular velocity, is d theta by dt. Therefore, we just take the derivative of what is given, which is d by dt of 0.130 t squared. And then once you get that, we substitute the value of t as 2.60 seconds. On doing that, we will get 2 times 0.130 and then 2 times 0.130 times t actually, and then we substitute the value of t to get 0.676 radians per second. So we have the angular velocity, that's part A. Now part B, we have to find the linear velocity, and we know the relation between them. That is, linear velocity is the product of omega and r. Now that we have omega and we have the radius, which is given as 8.40 meter, we can multiply the two to get the linear velocity as 5.68 meter per second. Now the C part, we have to find tangential acceleration. So there are two types of accelerations. Tangential acceleration compares with the linear acceleration. So in place of A, we have alpha. Now A is dv by dt, alpha is d omega by dt. So since we have the expression for omega, which we got in part A as 0.260 t, you just take the derivative of that and you get 0.260 radians per second squared. That means the acceleration is a constant. You see that the tangential acceleration is independent of the time, because the time factors out. And once we get alpha, which is actually alpha is the Alpha is the angular acceleration. I'm sorry about that. So alpha is the angular acceleration. And once we get alpha, we can find the tangential acceleration by multiplying it with the radius. So R alpha, that gives you 8.40 times the alpha that we have, which is 0.260. And that gives 2.18 meter per second. So the unit is meter per second because a meter per second squared because it's a linear acceleration. Now radial acceleration is also called what? Centripetal acceleration, and it's r omega squared, or omega squared times r. And when we use that, you get 0.676 times 8.40, which again gives 3.84. So that's how we, meter per second squared again. So that's how we work out this question. This question simply shows the connection between linear and angular quantities that we looked at during the review. So shall we move on to number 2? Here is question number 2. We've seen this in kinematics, where two objects are connected to a string passing over a pulley. And then when we did that question, we totally neglected the pulley. We did not even consider its rotation. But now in this case, we got to consider the rotation. As a consequence of considering the rotation of the pulley, what is going to happen is that the tension on both sides of the string will not be the same. Will not be the same. If we totally neglected the rotation of the pulley, then the tensions would have been the same, which is how we did it previously. So keep that in mind as we try to do this problem. Once again, we're given the two masses. The pulley is frictionless again, thankfully. The radius of the pulley is given, and it says when released from rest, the second block falls 77 centimeters in 5.4 seconds without the cord slipping on the pulley. So the cord is just moving along, it's not slipping. From that, we got to find the acceleration of the blocks. Since the cord is not slipping, both the masses and the pulley will have the same linear acceleration. And to find that, we need the free body diagram. We need to look at the forces that act on the two blocks individually. And we know that the force on block 1 is its weight down, tension up. And on block 2, the same two forces, its weight down, tension up. But since, block 2 is moving down, its weight must be bigger. Now, before we get to that, let's use the kinematic equation. Y is equal to V naught T plus 1/2 AT squared. And the first part is 0 because V naught, the initial velocity, is 0. You rearrange that equation and you would get the linear acceleration as 2 times, of course, y is in meters, that's why it's 0.77 divided by the time that has been given. And when you calculate that, you get the linear acceleration as 5.28 times 10 to the negative 2 meter per second squared. So now that we have the linear acceleration, we go to part B where it says, what's the tension, T2? Now for block M2, it's moving down. Therefore, its weight M2G minus the tension T2 up, which is the net force, is equal to mass times acceleration. That's Newton's second law. That's what I've done. And now manipulate that equation to make T2 the subject. And you get T2 is equal to M2 into G minus A. Mass of the block is 0.56 in kilograms. And since we have the linear acceleration, you can now substitute that value. I put it as 0.0528. And you get the tension. Now, when we come to finding the tension in block 1, we know that the tension T1 is greater. So T1 minus M1G is equal to M1A. I rearranged to make T1 the subject already and substitute the mass and the linear acceleration which we found out. And you get the tension in the string connected to M1 or on the left side. Of course, you see that that tension is less than T2. So the heavier mass, wherever it's connected, there the tension will be higher. And then the D part, we have to calculate the angular acceleration, which is alpha. And I already told you, since the cord does not slip, the linear acceleration of the pulley is the same as that we got for the masses. And so we can use that and then use alpha is equal to A by its radius. So alpha is A divided by radius. Okay. So we have the linear acceleration and we have the radius. Radius is in centimeters again, 4.6 centimeters. So I've changed that into meter, 0.046. And once you do that, you get the angular acceleration alpha as 1.15 radian per second squared. Now the E part, we have to calculate the rotational inertia of this pulley. And for that we use the formula torque is equal to I alpha, which corresponds to force is equal to mass times acceleration. Remember, I told you wherever you have mass in linear motion, you're going to replace it with rotational inertia in rotational motion. So that's why we use this formula. But since the tensions are different, we know that the right side the torque is clockwise, on the left side the torque is counterclockwise, you see, because they are trying to rotate the pulley in opposite directions. That's why to find the net torque, we got to take the difference. And since T2 is greater than T1, it's going to be T2 times R minus T1 times R. That's what I've done right there. So that's the net torque. But the net torque is I times alpha, so we can rearrange that and find I, which is the rotational inertia. Okay, so I is equal to T2 minus T1 times R divided by alpha. Substitute the values and we will get the answer. Now I'm moving fast because it's just a calculation part. And we get 0.0451 kilogram meter squared. So here is problem number 3. The angular position of a point on the rim of a rotating wheel is given by theta is equal to, that's a function, I'm not reading it. So you have theta in terms of t. We have to find the angular velocity, omega, at 2 different times. And then the average angular acceleration and the instantaneous angular acceleration. So I'm doing this problem to show you the difference between the average angular acceleration and the instantaneous angular acceleration. That is the main purpose of working this problem out. The first part we've already done before, from the given function, 8.24t minus that function, we can find omega by taking d theta by dt. So when I do that, 8.24, well, I've written it again, and that's going to give us 8.24 minus 2 times 3.08, plus 3 times 3.65 t squared. That's what we get. That's right there. And then once we get that, just plug in the values of time. Time 2.44. If you plug that into that, you would get the angular velocity at that time. And similarly, at the second time given, which is 8.89 seconds, plug that in and you would get the angular velocity at that time. So now we have the angular velocity at 2 different times. Usually what students will do is when they are asked to find the average, they would add these two and divide by 2, which will work sometimes, but not always. Therefore, to find the average angular acceleration, what we have to do is we have to find the difference. So alpha average. We have to find the difference in the angular velocities and divide it by the change in time, because that's how acceleration is defined, right? It's a change in change in velocity divided by the time taken. So that's what I'm doing there to find the average. So that's again slow. So when I do that, I would get, so in the denominator, I'm finding out the time, so that's why I've taken the time difference, and I get 118 radian per second squared. But when you're asked to find the instantaneous angular acceleration, you cannot do this. You want it at that instant. That's where you have to use calculus. So now alpha is d omega by dt. See, I've written it as d omega by dt this time. So you have to go back to the function that you had for omega, this one, and take the derivative of that with time. Okay, which is what I'm doing now. So you get d omega by dt. You see the difference there. And now you can plug in whatever time is given. And so it's at the beginning and at the end. So when t is 2.44 seconds, you get 47.3 radians per second squared. At the end of this time interval, you got to put 8.89. I don't think I've done that, okay? So that's how you do it. So you see the difference. Let's move to this next question. The next question is, a flywheel turns through 28 revolutions. So it turns 28 times as it slows from an angular speed of 3.0 radians per second to a stop. So the flywheel is stopping. But in stopping, it's making 28 revolutions before it stops. Just like a car, after you apply brakes, it'll move a certain distance before it stops. Same thing. But the problem here is that we'll have to change the revolutions into angle, theta. How do we do that? We know that one revolution or one rotation is 2 pi radians. Therefore, multiply with 2 pi. So if you multiply 28 with 2 pi, then you will get the total angle that has been described in that time. And we're using this equation. Delta theta is half omega naught plus omega multiplied by time. What is that? I'm just using the fourth equation in the review. Average angular velocity multiplied by time. So that's what I'm using. Now you know to take the average, you add those two, divide by 2. That's why you have that 1 by 2. Okay? And rearrange that to make t the subject. And then theta, remember, is 28 times 2 pi. So pi is 3.142. And yeah, I've written that there just to remind you how we get it. Divided by omega naught plus omega. And that gives 117.3 seconds. In the second part, in the B part, we're asked to find the angular acceleration. which is alpha. So now we use this equation because we have alpha in it. We know the angle described and we given the time, or rather we got the time, so we can use that, manipulate that equation, make alpha the subject, which is what I've done, and plug in the numbers. See, when it comes to the part where you plug in numbers and calculate, I'm moving faster, as you may have noticed, because you have the ability to pause if you didn't understand, right? So I'm trying to reduce the time for the video in doing that. So I've done all that, square it, and the answer comes out to be 0.0255 radians per second squared. Now the C part. How much time is required for it to complete the first 14 of the 28 revolutions? So it's just that time to complete the first 14 revolutions. So we're going to use the same formula that we used before in B, because now that we have the alpha, And theta in this time is 14 times 2 pi, because we are only looking at 14 revolutions at the beginning. The initial angular speed was 3.0, so that's where I have the 3.0. And since we're looking for time, t is the unknown. And also notice that I put a negative with this because for sure we know alpha is a deceleration. It's slowing down. That's why I put a negative there. And now it's math again. Do the calculations. You have a quadratic equation. You have to solve the quadratic equation. And usually a quadratic equation gives you two roots, two answers. So that is the quadratic. And you have to use plus or minus, I'm sorry, that's not plus or minus, I'm going to remove that. It's minus b plus or minus square root b squared minus 4ac by 2a. So this part is wrong, I'm going to remove that. Whenever I notice it, and there it goes. When you solve this, you get 34 seconds or 572 seconds, but we know that the time has to be less because it's the time for the first 14 revolutions. You see, the total time was only 117.3 to stop, so it can't be more than that. And so that's why the answer we know is 34 seconds. How about that? Shall we move on to the next one? Okay, so this is the last problem that I'm solving in this video. And this is an interesting one. You have a meter stick that is held vertically with one end on the floor and then is allowed to fall. Find the speed of the other end just before it hits the floor, assuming that the end on the floor does not slip. Now these kind of problems are totally physics-based, because you can see that there are no numbers. Well, actually there is one number, which is the length of the stick, which is a meter. That's all. So you have to have a conceptual understanding in order to be able to do this. We're looking for the speed of the other end, the top end, just before it hits the floor. You know it's speeding up as it comes down. So just before it hits the floor. And the idea that we're going to use here is conservation of energy. That is, at the beginning, the meter stick has potential energy. And then when it falls, the potential energy changes into rotational kinetic energy. So we can set mgh is equal to 1/2 I omega squared. But do not forget that the height of the meter stick is not 1 meter. That's its length. But we have to consider that all of its mass is located at its center of mass, which would be exactly at 50 centimeter, half of the length. So when we do mgh, we're going to have mg times half the length of the rod, which becomes equal to 1/2 I omega squared. And then for omega, we know omega is v by r, angular velocity is linear velocity by radius. And then with that substitution, we can find the linear velocity of that end, which is what is coming up. Okay? So first we find the angular velocity, but we also know that linear velocity is omega times the radius. In this case, the radius is the length, radius of the circle. You don't take half now. It's the whole thing. That's the radius. And then just plug it into that. Oh, there's one more thing. We need the rotational inertia of this rod. Now, where is the axis of rotation? The axis of rotation is at one end. At one end, this end, isn't it? So do not use I is equal to ml squared by 12. No, that is when it's rotating about its center. Using the parallel axis theorem, we would get the rotational inertia at one end as ml squared by 3. So that's what I'm going to use here. So there are many places where you got to be careful in working out problems such as this. So it's ml squared by 3. That is a mistake that I've made. Oh no. So you notice that I had made a mistake there. It's ml squared by 3. I put ml cubed by mistake. But when I substituted, it was ml squared in that place. So there's nothing wrong with the problem as such. It was just a mistake. My apologies for that. So this is, rotational motion and a few very important problems worked out.